manifolds in general, what we can calculate, what we can do, etc. So if you, first of all, let me try to give you a very short, condensed history. So if I start first thing, then what you know, I mean, the first paper on the subject was 1988, and this goes under the name of Donaldson-Witten theory. So first, Witten introduced this as just cohomological theory, so he wrote transformations. He said that it explains Donaldson theory, which is related basically to this equation, to instant-on equation. And later on, he came up with a twisting procedure, and this is basically n equal 2 twisted supersymmetric Young-Mills, and you can place it on any manifold. If you write this, if you look at this twisted thing, then what is important that Young-Mills section actually is written as whatever supersymmetry plus FHF, so topological term. So now what is important in this story, that why everything is nice, that this is a nice elliptic problem. And basically, this problem has a very nice modular space of instantons. And, you know, it's a great theory. People, I mean, conceptually, Donaldson achieved a lot of things, but practically, it's uncalculable. So it's very hard to produce very concrete examples. So this was first thing. Then if you move on, then more or less bunch of Russians in different combinations. So it's, I mean, quite often it goes under the name L, M, N, S. So M is non-Russian. So it's Losev, Moore, Nekrasov, Shatashvili. So in different combinations, they wrote a number of papers. And basically, the whole idea was to, first of all, take Donaldson-Witten theory. So not much can be calculated here. So for example, this modular spaces, even in R4, they are non-compact. So you cannot calculate volume. It's very hard to study certain classes there. So what this guy said that let's do equivariant version of this. Equivariant version of Donaldson-Witten theory. Okay? And then this already would make sense even on R4. And it was long, you know, program. So they started, I don't know, first papers came in mid of 90s, etc. And eventually everything resulted in this very famous work in 2002 by Nekrasov. So basically what he did, he constructed his partition function, and if you introduce equivariance, so you look at actually taking into account rotations of R4, then you can write instant-on partition function, which is just Z of one loop. I'm writing in particular way because I'm going to discuss it. Plus n from 0 to infinity, equivariant volumes of the modular space for sorry. Let me put n here, Qn. So for every topological number, let's say I'm considering simplest theory, just vector multiplet, etc. So I'm calculating volumes. So this is basically non-compact hyperkähler quotients. You can calculate the equivariant volumes. And that's what basically, you know, Nikita did. He calculated this explicitly, and then he took a limit, I mean, removing equivariance, and prove that it's, you will get Seiberg-Witten prepotential. Okay, so this was first formula, and then in fact, later in 2004, again Nekrasov, he said that if you take toric manifolds, so if you take toric non-compact M4, then you again can try to define the analog of the partition functions with some details. So his answer is conjectured, but the idea that on toric guys, you can write answer some sum over discrete data, and then you will have basically instant-on partition functions associated to every fixed points. So imagine that you have T2 action on M4. And you have fixed points. For every fixed points, you put his partition function. So there will be product of all fixed points. And then there will be some over some discrete data, which is basically what's called fluxes. And this is related to H2. It's related to some elements of equivalent second cohomology. So he wrote this, I think he gave a talk on some mathematical congress, math congress, and it's not on archive paper, but then math people actually took this formula seriously and proved this as a theorem. I think in 2008 it was proven, etc. But for toric and non-compact things, that's what you can prove. Okay. Then, if you go further in history, again, I'm oversimplifying 30 years of history, but this is more or less the idea. So again, if you think this is a calculation done in setting of equivalent Donaldson-Witten, so you take a Donaldson-Witten and you try to put consistently rotations, and things become so calculable. What is good that this is a very concrete object. It's complicated but concrete. And then next sort of big development was in 2007 by Paestum. So he took a force sphere. So you take, first of all, again, I'm discussing an equal to. So a priori, his calculation has nothing to do naively with this. And what he took super Young-Mills. Let me just think about vector multiplet. So you take a flat guy, then you covariantize, and then apparently, he did it, if you wish, ad hoc. You can introduce corrections 1 over r square in the action, and you can also do the same with supersymmetry. So you have sort of flat things plus 1 over r corrections plus 1 over r square. And then you would call it, this is, so he did it for S4. And then you can try to, localize things according to standard procedure. So, in a way it goes very similar to this, a bit more involved. And so now what you get eventually, that's he calculated, so his partition function. So I'm writing not answer of his original paper, but I'm writing which he wrote later on, and also there are some other authors, Hassan Michi and somebody else. So for the squash sphere, if I squash sphere by parameters epsilon, eventually he wrote that you have this integral over whatever Cartan algebra, dA, E minus SA classical. So it's a value classical, and then you have instanton partition function epsilon 1, epsilon 2, IEA modulus. So if you think about this answer, so you have S4, and you put instantons point like over North Pole and anti-instanton over South Pole, and you just glue them, these partition functions, etc. Okay? And then basically after he did it, there was very little work. So there is a lot of work on localization, but in principle, 4 dimensions is very hard. Exactly on which manifolds you can have supersymmetric theories, etc. So of course, this is, done by ad hoc, and it's very hard to actually generalize it with supergravity, etc. So for example, if you follow the program of Festucci and Seiberg, so those guys did, for example, full classification for n equal 1. For n equal 2, it becomes much more complicated, especially if you would like to have a toric symmetry. It hasn't been solved. So there are some separate examples, but that's very hard. So actually, it was a huge development in different dimensions, but not much has been done in 4 dimensions. But if you stare at these different answers, so if you stare at Paestum's answer, if you stare at this answer, which people, try to produce for toric non-compact thing. There were also some papers trying to do it for toric compact guys, for example, CP2. So the answer more or less will be the same. The only thing you tried now to integrate over this Coulomb parameters, so integrals, because in non-compact case, you regard these guys as a value of your scalar field at infinity. Anyhow, if you look at this, what is very natural to assume is the following guess. Make a guess. That if I would have any manifold, so, right? So let's do a stupid guess. So imagine I have a manifold, M. It's a vector field, which presumably should be killing. And I have my fixed points, isolated fixed points. Okay? And I just distribute instantons and anti-instantons randomly. So let's say here sits instanton, just do even different color. So see here sits instanton, anti-instanton, instanton, anti-instanton. So you distribute pluses and minuses differently. And then, of course, what you can try to do, you can try to write a formula which is like this. So you would say, okay, presumably my partition function is equal to, so maybe sum over some fluxes if there is non-trivial H2 dA, E minus S classical, and then I will have some sum over instanton guys, I, A plus KI, plus another sum of anti-instanton. So I'm writing very schematically. So this is just, so my V will be characterized. So my V, if I think about torus symmetry, will be epsilon 1, V1 plus epsilon 2, V2. In every neighborhood of my point, this looks locally as C2. I can read these equivalent parameters. I plug just in Nekrasov functions for instanton, anti-instantons, and then I integrate and I put everything together. That's the answer I would guess should be. I mean, if you look at this picture, that's what you would guess. Well, you can do whatever you want, but I don't know what it means. Okay, I will tell you. So this is what the answer you can actually, it's natural sort of to assume this answer. But the question, there are two things, is that do you have a supersymmetric theory on this setup? Because setup looks crazy. And then can you actually localize? And surprisingly, and that's why it took us so long, but surprisingly the answer, so the answer is the following. Yes, first of all, there exist supersymmetric Young-Mills for such a setup. Huh? I mean, the word twisting, forget about it. It's wrong. I mean, you just change the background. So because people start to think about twisting as something like I actually, in our paper, we remove all the word twisting. You put up special SU2 backgrounds in supergravity, and that's a twisting. If you don't have it, you have it. It's a specification of background. So there is nothing in there. Huh? Sorry? Donaldson-Witten will be the same. So what I'm trying to tell you, there is no difference between Donaldson-Witten and Paestum. There are different choices. You can have 2 points associated plus minus, a plus plus. So what I will tell you, it's a different supergravity background. That's it. But I mean, they're on equal footing. But I will explain you, in fact, that would be my goal of talk, to tell you what does it mean at the level of Donaldson-Witten theory, because you can ask what's actually we are doing, because there, I mean, supersymmetry is related to self-dual things, etc. So what I will tell you is that self-duality can be modified. And that actually comes from supersymmetry. But the answer is the following, that give me any killing vector with a fixed isolated points, distribute plus and minuses randomly. There exists supersymmetric theory. So we solved, we write all supergravity backgrounds, everything. And second is that it's in fact a general, yes, in 4 dimensions. Poincare. Right. But we are using Poincare, and then basically for Donald's, I mean, it's a special, I mean, different, very special specification of background there, etc. And also, let me come back. I mean, maybe you will ask a question. But again, as you can guess, Right. Right. But here what we are trying to do, let me make more, specify, because here we are very much preoccupied on calculability. So what we actually trying to extend, we are trying to extend equivariant Donaldson-Witten. So in equivariant Donaldson-Witten, it's important that delta square is not to 0, but to Lie derivative. So that's, otherwise we cannot calculate. So we are trying basically to generalize setup which Nikita is using. Okay. So this is first thing. Then second thing is that I will try to explain you the Donaldson-Witten theory. I mean, all this setting is actually related to Donaldson-Witten theory. The only modification is that you have to think, what does it mean self-duality? So actually, self-duality, we think this is the only thing you can do with two forms, but in fact, you can do something much, much clever if you have a vector field. And then if you do localization, that's the answer you get, localization. And sort of another moral, so that's what we hopefully, it will be, so first we put a paper which is more physical, and second we will put paper which is sort of more mathematical, but we are trying to, we will try to explain mathematicians what supersymmetry is doing, and there is this notion of transversely elliptic operators, which Paestum in fact used this. But why we like Donaldson theory is that it picks up us a very nice elliptic problem. But actually, whenever we have a group action, it's enough to have a transverse elliptic operator. So if I have time, I will tell you about these things. Okay? So let me now try to explain. Again, all my explanations are extremely schematic because it's, I don't know, it's around 200, 150 pages of the papers. Okay, so let me see what I want to say next thing. Okay, let me first start, because supergravity is not this very inspiring, but just you have to accept the fact that we actually can couple our theory and solve generalized Killing equations, etc. Let me try to give you a geometrical notion, because you can wonder what this self-duality does. So let me start with the following thing. What we are having vector field V, right? So let me introduce a form, which is G of V. Then there is the following very interesting map on two forms. So you take a two form and you map it to, just let's grab the formula, minus B plus 2 kappa HIV B. So let me assume for the moment that my V is non-zero. So no fixed points, I'm looking locally. So I have a two form, and I'm mapping two form minus this combination. So this is contraction with vector field, this is just wedging with this thing, etc. If you do the usual differential thingies, you will realize that this map has two properties, m squares to 1, and m sends two self-dual forms to anti-self-dual forms. It's a trivial calculation, you can check it. So then what can you do with this map is the following. So let me draw this picture bigger. So imagine I have my manifold, M. Sure. No. I'm just, right now, I'm pointing algebraic property that if I have V, I have this map. But this map is defined when V does not have, fixed points, zeros, right? But I'm going to use this map locally only. Okay? So now the idea that, let me take a manifold. I have a V fixed points. And then I have a patches. So I have one patch, and I have another patch. So let's say in this patch, sorry? No boundaries, no boundaries. No. So here I associate plus. So let me put attached to this guy self-dual forms on this patch, or alpha. And here I associate minus, so I attach anti-self-dual forms on minus on this patch. On this intersection, I produce UMAP, which is well defined. This would be my transition functions. And I keep going. So for example, if my nearby patch is here of the same sign, so it's minus, then I can choose here, use just identity map. So the only thing, of course, to make sure that you glue a bundle, you have to make sure that it satisfies cocycle condition, and it does. And then you will get, so if you have a vector field on the manifold, you can glue a new bundle, which locally would look like a self-dual, anti-self-dual forms. So we start to call this bundle, so our notation's a bit funny, so we call this bundle like this. So this is mathematical definition. You can, of course, be a bit more simple-minded. And actually, so this is new self-duality. So I glue them. So in Paestum cases, basically the following. You take a sphere, you do the cover, north pole, south pole, you attach to the up self-dual forms, down anti-self-dual forms, and somewhere on an intersection you use vector field to glue them. And because on intersection vector field doesn't vanish, this map is well defined. You get a bundle. Now, if you want to be a bit more simple-minded, and this is actually what we need about these maps. So actually what you have m square equal to 1, and then you have m star plus star m is equal to 0. So you can construct sort of a generalized new star. This will square to 0 as long as alpha square plus beta square is equal to 1, right? So what you will have the following projector. So you can introduce a projector, I don't know, P plus, new projector which would look 1/2, and then you will have these guys, 1 cosine of rho star plus sine rho of m. Now the only trouble here, if you use this logic, is that you have to remember that this map m is not actually well defined at fixed points, okay? So you have to worry about the thing. But what you have to guarantee that actually this term is, so rho is just some function. What you have to make sure that this term is well defined. So as you approach fixed points, rho should go to 0, I mean, in such a way that to make it finite. So you can see, you can do it. I mean, we did a concrete constructions, etc. Again, I'm telling you things backwards. We actually derived it from supersymmetry and then came up with geometry. But of course, this is much better picture. So this projector actually, at fixed points, you can see that this term goes to 0, and your cosine will be either plus 1 or minus 1, depending which function you choose. So at fixed points, this projector collapses either to self-dual projector or anti-self-dual projector. Okay, and this term disappears. Away from this, of course, it looks as a mixture. So this is a projector. And the only thing is that I have to make sure that the only subtlety is that this is well defined. Okay, so this is a generalization of notion of self-duality. So actually, so supersymmetry is extremely, this is the phrase which Martin taught me is, I mean, he told me about superfields, but I like supersymmetry is smarter than we are. So this is exactly the thing when supersymmetry is smarter than we are, because when you look at the things, I mean, in a way you start to get all these very exotic notions, etc. But at the end of the day, we are trying to supersymmetrize a normal Young-Mills with normal kinetic term. And so the bounds, for example, you typically have, right? So, you know, this bound very well, or not bound, just identity. So if I take a Young-Mills section, this is the same as P plus F, right? up to topological term. Okay? So we have exactly the same type of identity here. Again, it's a simple algebra to work out. So because of property of this guy, it actually gives you a decomposition of your two forms in orthogonal spaces. So there are a lot of nice things which comes automatically. And what you get there, again, let me write schematically. What you will get there, that f squared is equal to some positive functions p, this omega plus f, equal to 0, and this plus another function IVF square equal to 0 plus some lower derivative term, basically analog of topological terms, lower derivative terms. So it's another decomposition of the thing. So mathematically it's basically related, because if you put a gauge fixing, you here have a Laplacian. And you take a square root of Laplacian, so you basically take a one elliptic problem of second order and decompose an elliptic problem of first order. So here you do the same thing, but now it happens at the level of transversal elliptic problems. But you have this identity, and basically supersymmetry is exactly doing the decomposition of the things. And again, this projector, I mean, this is not the way we came across this. So it comes out of supersymmetry. Okay? So just comment, whoever knows Donaldson-Witten theory, So if you look at the original paper by Witten, then there are all these fields, I think A plus, there are two scalars, and there is these guys, and then there is these two form fields. So, I mean, this is like in Donaldson-Witten theory, connection, fermionic one form, scalar, again, this is scalar but odd, this is even, and then you have two forms. You have odd to form and even, and you, in Donaldson theory, you decompose self-duality. So now the only difference, and that's you can actually check in Paestum, you change this notion of self-duality. So you put this exotic self-duality here, which is given by this data. So that's the theories we are doing, and as you can see that, so Paestum theory, it's exactly when you just change self-duality to this exotic notion. Okay, let me make some comments about supersymmetry. Again, my comments are very schematic. Susie. Yeah, I mean, for examples we worked out CP2, I mean, these things. And also on CP2, so what you can do many supersymmetries. You have three fixed points, plus, plus, minus, 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 plus, etc. So you can write projectors. And the theories differs quite a lot. So, and yeah. And then originally what we did, so how we came across, we were also doing a lot of examples by reduction from 5D, when it's much easier to solve some killing spinor equation, then we reduce down, etc. So another example is S2 times S2, connected sums of S2 with S2, etc. Fixed points, it should have fixed. So we are not looking. Oh, you're right. Right. So to discuss this projector formally, you don't need to assume that it's killing, it should be global. But of course, once you decompose in the spaces, it's important that these spaces invariant under V, otherwise the algebra wouldn't work. So that it's killing. And of course, exactly from supersymmetry, you know that always killing will come about. So let me talk about supersymmetry briefly. So I have a vector field V killing. And what I need to do the following. I have to take V square and decompose this into functions, S tilde. And this should be positive functions. And the only thing is that S tilde is 0 at plus fixed points. And S is 0 at minus fixed points. So I need to make these choices. And then actually what you can do, so you can introduce spinors, so I'm using standard notations with whatever reality conditions, but what I want to schematically write that I can have different bilinears of my spinors. So this is SU2 index, I construct S over 2. So this guy specifying me so this would be 1 over half VB. I is a SU2 index. Alpha is a spinor index. Alpha and alpha dot. I'm using standard notations. So if you don't know about, ask Martin. I learned from him this stuff, okay? So now, and also what is here interesting that we actually use the same idea. So the challenge is actually to prove that there is always supersymmetry. So we have to go to spin manifold. So by the way, one comment is that when I'm discussing this theory, I can do it for any manifold with a Killing vectors field. If I want to talk about normal supersymmetry, of course I have to assume, if I want to be decent, I have to assume that I have spin manifold, I put reality conditions, etc., etc. So CP2 is outside of this example since it's not spin. But what we are doing is the following. We have to find out, we have to prove that there are globally existing spinors which satisfy this bilinear thing, and then they also, on the top of this, solve generalized Killing equations. So the funny thing we actually are doing is we use the same idea like with the form, so we locally try to solve our problem like a topological twist, and then we try to glue them. And so basically, what we have to first argue, and I'm not going to do it here, but just believe me that you can prove on spin manifold with this choice, you can always prove that the spinors exist. And then you have all this huge amount of supergravity fields. I'm not expert. Again, Martin would know more. I will not even bother to write them, but you know, there are a lot of fields: metric, SU2 fields, gauge fields, scalar, two-form, scalar triplet, again two-form, etc. So you can fix them, and again, we are solving them backwardly, and full solutions, I mean, some of the solutions we put in appendix occupy half page. But in a way, this is very useful in this framework. When you know what to get, you get. Because we actually have just to show that generalized Killing equations can be solved. Eventually, and also what is important, when we fix supersymmetry background, there are ambiguities. So not everything defined uniquely. There is like, it's defined up to whatever tube form, which contracted with V0, etc., etc. So there are many solutions, more than one. Eventually, what we argue at the level of partition function, that things depends only. So when I distribute my pluses and minuses, this is only data on which partition function actually depends. So you can actually vary backgrounds, and the enters reverse the exact terms, so they do not contribute in the answer. Okay, so this is supersymmetry comment. Now, just another comment for people who love supersymmetry, that actually, if you construct the spinors and they satisfy Killing equations, then actually there is one-to-one map which is invertible between, if you wish, Witten variables, which is A, psi, phi, phi, eta, chi, h, and the standard supersymmetry multiplet, which is A, x, x bar, lambda, I bar, lambda I, dij. So you can write explicitly map one-to-one with these guys, and eventually everything, all complicated supersymmetry under this map, goes just to equivalent version of Nekrasov, with only difference that these guys satisfy now generalized self-duality. But again, in checking algebra, it's not important. It's important that they belong to invariant subspace of two forms. Okay. Right. Any questions? So what you need to construct supergravity, you have to split, basically to take a square root of v square in this form, two functions. Some function will vanish at some point, some another. So at the level of spinors, one bilinear will vanish, for example, for minus fixed points, another bilinear will vanish for plus fixed points. And that's exactly telling you where you will have instant or non-instant. Now, if you, so v square, of course, can be decomposed in many different ways. So it will give you automatically different supergravity backgrounds, and they're not related by any supersymmetry. Of course, as a bundle, the way when I, for example, defined here, I mean, there are some choices involved. But you can, for example, choose that if you want to choose this row in a different way, but you don't change this allocation plus or minus, you always can come up with a orthogonal rotation in space of forms, which will bring one bundle to another bundle. So bundles are isomorphic as the distribution of pluses is the same. It will be determined by these functions, or by your choice, right? I mean, it's given by vector field, right? So my data is, I'm not saying give me any manifold. I'm saying give me manifold, give me a Killing vector field with isolated fixed points, and then give me a decomposition of Killing vector field, its norm, in terms of two functions. And this function vanishes on some points, and this function vanishes at another points. Once you give me these things, I can write for you everything. Okay. Right. Absolutely. Now, if you give me another distribution, it's another theory. It's another supergravity background. It's another theory. So, of course, I'm saying that if you look at S4, if it's plus plus, it's one theory. If it's plus minus, it's totally different theory. Okay. Right. So let me just make some. Again, I'm skipping a lot of details because actually proving all these things, etc., it's highly technical. But I mean, once you know the answer, it's straightforward. So another just comment that actually supersymmetric, for example, Young-Mills can be written in very similar form as, so it's delta exact. But here, instead of topological form, you actually will get this guy, f plus psi plus f square, which some equivalent form omega 0, omega 2, omega 3, 4. So now actually this form is killed by d plus iv. And this topological term, I mean, now you understand this inequivalent thing. It's independent of the class. So this is equivalent, if you ignore fermions, this is equivalent second Chern class. It's paired with equivalent guys here. So now actually in concrete Paestum calculation, this is a very concrete thing. So what you have below, you have a cosine of theta plus concrete 2 form plus 3 volume form on sphere. So you can see the leading term here, actually. So it will be cosine theta FHF. So even without doing localization, you can see that your theory is supposed to have a term which would flip things. So, you know, sort of if you look at the bundles with one fixed Chern class, and I mean, on the north pole, if it's localized, they will tend to come with the pluses, on south pole, they will tend to come with the minuses. It's not a proof of localization, but it's basically telling you that there is a purely cohomological reason. And in fact, what is important is that take any positive volume form here, you always will have a here flipping behavior. Again, it's purely cohomological reason. So there is a lot of ambiguities you can introduce, but for example, if it's volume, it will flip. So actually, for example, Paestum theory and all other theories depends on very little. So, and again, it's basically a generalization what Witten wrote. The only thing is that now you just promote everything to equivariant guys. So before it was just F wedge F, that's it. Now you have scalar, which, I mean, this guy forms equivariant connection because one of the conditions which comes in supersymmetry is this condition always. So it's actually equivariant connection. And this is concrete equivalently closed form, which one can calculate, depending on examples, okay? And then actually, this is I'm skipping, but you can try to cook standardly localization argument and try to localize. So there will be now, unlike Paestum, there will be two types of contributions. They will be point-like instantons, but they also will be contributions related to fluxes. So highly reducible contributions related to H2. So again, we basically cannot say exactly which fluxes. We get complicated PDEs. We try to analyze them partially, but we cannot say it in general. So we know they will be fluxes, but for example, if you give me distribution of pluses and minuses, I cannot actually tell you exactly. In some examples, like in CP2, we try to solve these equations. We can do it sometimes, but in general, we don't know how to do it. So let me make some more philosophical remarks about why things work, and so for my math friends and what's going on here. So typically, if you talk about what people call topological field theories, although personally I prefer this name, which would be cohomological field theories, because they are not actually always topological if you need vector field, etc., etc. So I prefer cohomological, but the standard setup, if you will look at many papers in the 90s, the idea is the following. The good problem is the one problem which is elliptic. If I have an elliptic problem, I put some fields. Elliptic problem typically comes from supersymmetry, and then I have a theory. And always the idea is the following, that if I have my Laplacian, I basically take a square root of Laplacian, for example, like I do in S2, right? So I have a Laplacian, it's a second order elliptic operator. If I take a square root in clever way, I will get, for example, Dalbo operator. And this is first order elliptic operator. If it's an elliptic problem, everything wonderful, there is nice modular spaces, we can calculate everything, or even if we cannot calculate explicitly, the theory is well defined. Okay? So what's the difference with here? How do we change our paradigm? So what do we like about elliptic operators? About elliptic operators, we like that their kernels and co-kernels are very small, right? So I mean, the space of solutions is very little. And what you can do, for example, if you look at this very trivial example, imagine, let me do the following thing. Let me take S1 times S2, okay? And now this is U1 action. Now what I can write for you again, the same operator acting on the functions, or del bar acting on the functions, but now of S1 times S2. So now, of course, a priori, this operator does not have a finite dimensional kernel in a very dumb way. But what is very important is that if I look at this kernel, I can decompose this in terms of representations of this guy. So transversely to my orbits of my group, this is actually elliptic. So this is a definition of transversely elliptic. Again, very primitive. Right. Right, but I can decompose in representations of U1, right? That's the whole thing. Yeah, it's countable. I mean, the whole idea is that, you know, this is very simple thing, is right? So what's the power of equivariance in a very dumb way? So if I give you Dalbo operator del bar on C, right? I mean, what's its kernel? All holomorphic functions. But what I can do, I can count them. So basically, I can write for you generating function with respect to representations. because I have a U1 rotation, right? This corresponds to constant, this corresponds to 0, this corresponds to zeta 2, etc. It's a different U1 representations, okay? And this is equal to 1 minus 1 over t. So that's another way of counting. So it's transverse elliptic, but again, this is very primitive. You can covariantize, for example, take S3. So you can define a horizontal Dalbo. So you, for example, take Hopf vibration, you have a rotation, you introduce connection, and you can define this operator. Now, it's a transversely elliptic. And again, it's transversely elliptic, sort of transverse to the fibers, it's elliptic. If you look at the kernel of this operator, it has a very nice decomposition in terms of finite dimensional representations. And again, this is very easy to analyze. You can, I don't know, take your zero forms, decompose them, or n bundle. It's the same story like Matai was talking about in his talk, okay? So this is example of transverse elliptic operator. But however, what is very important that in these stories, what we are doing is the following. If I would write a Laplace operator here, it's actually just this plus this, right? So I take a normal Laplace operator, I write time derivative over this and equal to this. So here I will do the same thing. It may look covariantly a bit more complicated, but it's still the same thing. So what I'm doing is, and this is in fact one of sort of alternative definitions of ATIA, that this operator, if I will be able to take my operator and compose things in this way, and this is second order elliptic operator, then this guy is automatically transversely elliptic. So in a way, supersymmetry is telling me how to decompose the things in consistent way. And that's exactly what our projector is doing. So again, this is very primitive. It's a complicated subject, but this is the idea mathematically. So if I, for example, look to, I can write for you for instantons what's going on. So if I look at instanton standard ones, so I add gauge fixing. So this is elliptic 4D problem. On M. Oh. I can do, first of all, something very stupid. That's originally how one can get. I can actually repeat the same trick. So I'm just taking S1 times M4. And I leave this problem to transversely elliptic in there, in one dimension higher. So I will now put a self-duality in horizontal directions. So again, I have very... And then again, here I will write for you something non-covariant, but it can be covariantized. For example, A alone S1 I can put to 0. So this is formally a transverse elliptic problem, but it's not written in 5D. If you want, you can write these things in better terms if you want to covariantize. So this is 4D. If I want to actually covariantize everything, I will write this. So naively, I would like that component along this S1 is 0. But it's too many conditions, that's why I put D dagger on this. So actually, you can try to write the symbol of this operator, and this is exactly what's written in Paestum paper. But he writes this for 4D. Okay, so this is very trivial lift exactly in the same way. Like I took elliptic operator, I added circle, I push it up, I get transverse elliptic problem. So what I can do here, right, if I decompose my A in the modes, then in every mode the problem looks good. Now what I can do is the following. So if I would, so this V here, let me call R. So it was originally S1, here I lifted. But let me now push it down, but twist it a bit. So imagine that on T4 I have some action, T2 action. And I will reduce things along this leg and this leg. So then I will bound in 4D to get a transverse elliptic problem. And this problem actually will look as follows. So P omega plus F minus whatever D some function. I mean, it's one of the choices, scalar equal to 0. And I will get dA equal to 0. Sorry, I think it's bit different. I don't want to lie, IV star d phi, I guess. And then there is a d dagger of IV plus d minus cosine of omega. So if you do this, so this is a transversely elliptic problem in 4D with respect to this torus remaining. In fact, if you calculate an exactly symbol of this operator, you will get a 5x5 matrix written in Paestum paper. So it's actually, it's not the way he did it, but actually if you want to understand what he's doing, you take elliptic problem in 4D, you push it in 5D, you tilt it, and you push it back. That's it. That's why he has this cosine and sines. Because the way when you tilt it a bit, you have to watch the vector alone, you reduce how it corresponds. It can be parallel or anti-parallel to this S1. And that's why you get instanton or anti-instanton sometimes. So actually I started with instanton here, but here I can get both instanton and anti-instantons because it corresponds to relative sign here. Okay, and again, all these exotic problems actually, if you square them, there are some subtleties and related to gauge fixing, etc. You always actually will get a normal Laplacians, normal second order operators. So supersymmetry actually is telling you how to take a normal theory and decompose in first order operators, but because you have killing guys, you actually do not take a square root in a down way. So you just don't write that Laplace is equal to whatever d plus times d minus or d plus. You write something more complicated because you have a Lie derivative and then you write this. And so what is important that again, kernel of this guy is an infinite dimensional, but it decomposes very nicely with respect to whatever U1 or T2 you have. So that's about math. And so I don't know, I think I will stop. How much time do I have? Who is the chairman here? Huh? 5 minutes. Okay, let me tell you the thing. I mean, so actually, and this is general feature not only for 4 dimensions, etc. But all your supersymmetry actually, so when you localize, so supersymmetry is very complicated. When you localize, you care only about linearizations. And actually, what you can see in all calculations, linearizations actually gives you a sort of double complex. So if you want, I don't know, I mean, I can write an old-fashioned way. So imagine I have something like this. So I have a boson goes to fermion, fermion goes to some linear operator. Then I have here delta chi equal to h minus idx, and delta h equal to r. It's a Paestum-inspired notations, psi. So this is boson, fermion, fermion, boson. So you have two parts of the complex. So if you write this in terms of this, you have x, chi, you have psi, you have h, so you have this operator is d. Here I can put zeros, so I'm writing as a complex. And here I have operation of R0, R1. So whenever you look at linearization of supersymmetry, and this is always the case, is that actually the only thing is calculable when this would be typically Lie derivatives, and this would be transversely elliptic complex. Elliptic complex. And that's what always supersymmetry does to you. Now, what is important here to realize, and again, this is a very constructive exercise, because you can think, oh, crap, why do I have these complicated things, etc. But if, for example, you will write, I'm naively Beer's exact term, which would be psi of R0x plus chi h. And then you take just delta of this, and you integrate h as you typically do. You will get this x minus R0 square plus 1 over 4 d dagger d x plus psi chi I0 I over 2. It's very nice calculation and very trivial in a way, but 1 psi chi. So what I'm trying to stress that what I did, so my supersymmetry is like, think of first order, but this is analog of Laplacian. This is analog of Dirac operator. Okay? So this is what some people in localization do. They don't use index theorem, so this is what we can do. We can actually try to take these guys and calculate, this goes down square root of determinant, this goes up square root of determinant upstairs, etc. But eventually there will be a lot of cancellations, except that when you calculate things, what will be left. So supersymmetry is telling again how to decompose these guys. So if you want to go to Witten's story, these guys are 0. That's why his transformation squares to these things. Because if you check here, this sector it squares to R0, in this sector it squares to R1, to some linear. If it would square to 0, that's what would be. Exactly. So I will decompose my second order operator in two operators. And in Witten's story, basically, ideally you have to get just 1 or minus 1. But here you get basically characters related to your representation. So if you calculate a partition function here, you will get, again, do it if you want, determinant 1 over 4 minus R1 square plus D dagger 1 over 4 here, and then here you get determinant of 1 over 4 minus I0 square plus 1 over 4 d dagger d. And in fact, again, this is what you will get if you don't know about localization, but if you watch how your eigenvalues cancel out, you will get R1 here on the kernel of d dagger and determinant of 1 over 2 on the kernel of d dagger d of R0. So this is, that's what people do when they do localization. They arrive here right away. If you actually will just do, localization, but then you just do, expand over quadratic things and do actual second order guide, that's what you will get. You can convince yourself that, outside of this kernel there is full cancellation, then you get this. And then what is left, it's exactly to make sense of these things. And it's important that these kernels are decomposed in a normal way with respect to these operators. If they decompose normally, then you can write the answer. And that's exactly an example of transverse elliptic operator. If it's not transverse elliptic, then you are gone. But again, the transverse ellipticity, the fact that this is well defined, it's actually guaranteed by that this decomposition is actually good. So this should be a proper thing. So, and again, it's basically supersymmetry. We are supersymmetrizing always normal operator. We start always from F squared term. I think I should stop here. Thank you. Right. Gluing, so parameters you identify purely from knowing, how your torus acts in neighborhood of every point, etc. So the main thing is this shifts. So when you have non-trivial things, for example, CP2, S2 times S2, you will have fluxes. And that's a tricky thing. We know they're there, but we don't know how exactly solve them. So, typically, already Nekrasov guessed that it should be some sum of equivalent cohomology with some stability conditions, etc., but this is all words. We didn't solve it. In some examples, we got PDEs, we don't understand this meaning, etc. One of the biggest, so there is a conflict between older school and younger school of localization. So people, calculations and localization is much better defined on non-compact manifolds. So actually, all Nekrasov problems can be gone and regularized by non-commutativity. So Paestum did not derive anything. He guessed the answer. And I mean, because how do you deal with singular configurations, right? I mean, point-like instantons. I mean, Nekrasov knows how to deal with point-like instantons. You put on non-commutativity, etc., etc. On S4, you cannot do it, actually. So compact spaces are very hard to deal. There is no systematic approach. And so there is this sort of thing. So actually, one of the biggest challenge in a compact thing is that to understand how to deal with this singular configuration, but we are cheating, I mean, so you have to be aware. And the author is aware that, I mean, his result is sort of not a proof. It's a plausibility result. There is AGT correspondence, etc. But a priori, right, he analyzed smooth, and then I have a singular configurations. And this is problem in all dimensions, starting 4, 5, 6, etc. Only 3 is innocent. And again, it's innocent in a particular way. You're welcome to understand. No, we suffered for 2 years to fix all science here, etc. So I mean, we don't know. But one comment is here that I think because we now can cover a lot of manifolds, because before what you did, you fix 4D side, and then depending, you change 2D side, and you got different theories. Now, because you have these things, you can do other way around. You fix 2D side, and you play with 4D side. And then it means that different 4D things should correspond here, and then you have to come up with some tools like in AGTS duality, when, you know, paint decomposition is compatible with S duality on 4D. So here's the same thing. But I think now, I don't know, but in principle, there is a possibility to revert thing, that you change 4D side and you fixed 2D side, I mean, in terms of manifold, but you have a different 2D theories. I think it's the same story. So as if we believe in string theory, I mean, or in quantum field theory, everything should be compatible. So of course, you know, 2D theory in this correspondence should know whatever is going on with 4D manifolds. But again, all our 4D manifolds should have some torus action. I mean, otherwise, we cannot say anything.